may come out. Okay, so but in this case, of course, that when you want the cascade, so there actually higher energy is required. Now this is another important part, the sputtered yield. What is sputtered yield? Number of sputtered atom divided by this number of incident ion. So number of incident ion means number of argon ion, whatever actually hitting on the target, and number of sputtered atom, number of sputtered from this target, how many number will come out. So now this S is very important, and S depends on what are the parameters like type of target atom, so S depends on type of target atom, then binding energy of the target atoms, and of course this is also important because every material has a different binding energy, so that is very important. And type of target atom, that is actually, I mean, it's kind of argon more or less fixed, relative mass of this ion and the atom, so that relative mass is important because that is actually, I mean, like if we fix the ion, at least that target atom is changing, so that's why this is important. Incident ion energy, so whatever that incident ion energy, that is I told very important, because in which case sputtering will happen and which case ion implantation will happen, so that is also will be decided by this incident ion and angle of the incident of this ion. This is also important. And S and can be range from 0.1 to 10. And in the first picture you can see that in 1000 or 1 kilo electron volt, there actually you are getting this is actually incident energy. So if you change that incident ion energy, so in this particular energy you are getting this maximum yield, sputtering yield. And in this case actually 60 to 70 degree angle, you are getting that highest yield. 60 to 70, this is actually that heating angle or that incident angle of incident ions. Okay, so these are actually very important parameter. And now actually this angular and the energy distribution of this ejected atom. So in this case actually what will happen in sputtering, if it's follow that cos theta dependence, because from the target actually atom will eject, now atom will go, so there are actually millions of atom is coming, and that is actually, of course, it will follow some trajectory, and that is actually this cos theta dependency we called it. So if it's happening that in physical vapor deposition, we have seen that it's a cos theta or cos to the power and theta dependency, depending on the point source and the surface means source. You recall that your previous class. So this, if it's cos theta dependency, so this is the path it will follow. So low ion energy, isotropic flux, and better step coverage. So better step coverage means, suppose that there is a step, so the step coverage will be better. But if it's cos to the power n, in that case it will be more directional, so high ion energy, higher directionality, and poor step coverage. So if you want to have a poor means steps, suppose that whatever substrate is there, that is not flat, some trench is there. Like if you go for, let's say that, I mean, field ion beam, so you may get some nano trench. So that trench actually, if you want to deposit the material, so in that case actually maybe that you have to think for cos theta dependency. Now how it will come, like actually that, just let's go through. This sputter atom have relative small energy and typically 2 to 7 electron volt. Okay, but in thermal evaporation, these values are even smaller, 0.1 electron volt. So what is that one? This sputter atom. So whatever atom from the target to substrate is coming, so that energy of that atom is 2 to 7 electron volt. But in case of thermal evaporation, it's 0.1. So that is the reason in 0.1, that is the reason that we need not need to be worried about that cos theta or cos to the power n dependency in 0. Because this is is actually, energy is very less. But in sputtering, that is not, may not be a big problem, but still there is some dependency is there. So number distribution as a function of energy is like actually Boltzmann like, and and this angular distribution is actually cosine like, and it depends on this ion energy and the target type and that crystallography. Okay, so these are actually different things that whatever will decide the target type. So we, according to the target, like if it's actually very strong energy, so of course that actually it will require, means whatever that energy will be less, whatever that coming out this atom. And if it is actually loosely bound, then actually of course that it will be, it may acquire that very high energy. Okay, so these are things are there, and crystallography of this actually, the target, these are actually important, and that will decide finally that it will be cos theta or cos to the power n. So sputtered atom from the target makes their way on the substrate through diffusion. So why diffusion? Because that in between maybe, there is a, like actually plasma region is there. So through that plasma it will come. So that's why through the diffusion, and these ions and that neutralize. So there is actually basic difference. Actually in this sputtering case, what will happen, that whatever from the substrate, if you see the picture, so this is actually the target. From the target, actually, it will come to the substrate. So in between, the plasma is there. But in case of physical vapor deposition, in between, nothing is there. So in physical vapor deposition, our target is that mean free path should be as maximum as possible, so that no collision will be there and it will come. But in this case, what will happen? Whatever ejected atoms are there, that is actually having little bit higher energy, much higher energy than physical vapor deposition. Now this will actually come through that plasma, and that's why actually this last class one student was asked, that is actually, some sort of true, but it has higher energy, so there will be not a problem, and millions of atoms will be coming. So and it will reach to this substrate. It will diffuse through this plasma region. Now this ion and the neutralized gas atom may also embedded on the substrate as impurity. So this argon plus ion or the neutralized gas, some neutralized gas, that is also can be, can come to the substrate, and it may act as impurity. There is a possibility. And then ion incident on the substrate may also re-sputtered on this, on the surface. So this argon actually cannot on this, there is a chance on that on the substrate, but that is actually very rarely will happen, because argon actually is coming due to this opposite terminal attraction force. So that is actually is may not experience on this substrate side, but there is a chance. And chemical reaction also may happen sometimes, and in reactive plasma, reactive sputtering, that chemical reaction is actually very common. Now the deposition rate, so it is proportional to the sputtering yield. So this deposition, so sputtering yield is high, means deposition will be high. So an optimum pressure exists for high deposition rate. So this is, we can see the deposition rate. So higher pressure means more collision of and ions. So this is if we maintain very high pressure. So more collision, and low pressure means that less scattering. Okay. So that is actually, these are things are there, and you can see the deposition rate is actually optimum pressure. So this is low pressure, this is high pressure, and this pattern actually is happening here in this region. So this pressure actually have to make it balance. If you go for too low vacuum, then it will be a problem. This, like actually mean free path will increase, and the lower pressure means that less scattering. These things will be there, because we need to generate the plasma also. So to have the plasma, we need sufficient that argon, that one. But if you make a high pressure, then more collision, and this collision and ions, then also that there will be a problem, that whatever ejected atoms are coming, sputtered atom, that is also may have some collision. So these are the problems are there. So that's why if you increase too much pressure, then again sputtering will decrease. So the deposition rate, you can see that deposition rate is the optimum this organ pressure you are getting that highest deposition. So this alloy composition issue, that this alloy composition issue actually in sputtering there is no as such problem. So you may get whatever that your desired composition, that is actually it will intact there itself. Compound issue, that while most of the previous discussion is applicable to this compound, there are an interesting issue if the target temperature is too low. So target temperature ion bombardment can result in amorphization of the crystalline target and isotopic sputtering. So target temperature that has also role. So if target we are keeping at low temperature, so this isotopic scattering means actually it can move to any direction this atom, and that's why this amorphization of the crystalline target we called it. But if we increase the target temperature, it will anneal the surface at its sputter, and thereby it's keeping the crystalline structure and a more directional sputtering. So whatever that from the target, the sputtered atom that is actually will deposit on the substrate, and if I keep the substrate at room temperature, then their case also some amorphous structure we may receive if you do the sputtering at low target temperature. But if you increase the target temperature, you may get the crystalline structure on the substrate and directional sputtering you may observe. Okay, because why it's happening, like if you have a temperature, so temperature means actually this target atom will acquire some energy. So when it will from the target, it is coming to that substrate, it will have energy, sufficient energy, so it will rearrange it, it will form there the crystalline structure on that substrate. Step coverage and the film uniformity, already I talked about the angular distribution of the sputtering depends on the pressure. Lower pressure result in more directed flow, which results in less uniform film, and higher pressure result in more isotropic flow and that better coverage. So this is actually, like pressure has impact on that cos to the power n or cos theta dependency, and this uniform film also require that larger target. So pressure actually you have to optimize that, in which case actually you are getting that better like actually uniform film. And uniform film also require the larger target. If you have a larger target, then what will happen that this atom will sputtered out from the big area, and then actually whatever the problem of this like uniform film, okay, or the thickness variation, that is actually will not be there. But this is actually that larger target you don't have liberty much, because there is whatever that your target holder is there, it should not be larger than that. But in this pressure, actually in every deposition you can control the pressure. So that is why actually that if you just see if you do this sputtering, people actually do the different pressure and do the sputtering, and then observe that property of the film or the quality of the film by X-ray diffraction, or let's say the scanning electron microscopy, or maybe X-ray photoelectron spectroscopy, photoemission spectroscopy. So by this measurement that you can check that actually how is that quality of this your film. And then what are the parameter like organ pressure, that is very important. So this initial pressure that is actually will decide that how much plasma will generate. Then the sputtered voltage. So sputtered voltage means it's between that anode and cathode, that voltage, whatever this one sputtered voltage. So that sputtered voltage also will decide that actually sputtering will happen or ion implantation will happen. Then substrate bias voltage. So some substrate bias voltage also there, that is also important. Substrate temperature. So substrate temperature has a role that to decide that actually the quality of the film. Particle energy, so increases with increasing the sputtered voltage and decreases with increasing that substrate bias, and decreases with increasing argon this pressure. So particle energy means whatever this argon plus is actually hitting on the target. So that is, we called it this particle energy. And now actually with this one, this I just finished that overview of the sputtering and this classification of the sputtering. There are 4 different classification: DC, AC, RF, reactive and magneton. Reactive I'll start first and then followed by DC, AC and magneton. That is maybe your after your that mid sem, then I'll go through. It will be taught. And today's actually exam, that it will be actually very introductory of sputtering. But up to today's class, it will cover in your um, like that after mid sem. In your mid sem actually, up to today's class, it will cover. So with this actually, I'll take the download that attendance. If you have any questions, very fast you ask. Otherwise, that we can wrap up. And I'm sorry, actually, it was a bit late, but no problem. Any questions? So please do ask. Otherwise, wish you all the best for your today's quiz. No question? Okay, then bye. Thank you.
Thank you, sir.